Okay, in the previous lesson we have looked at equilibrium in terms of the balance of the forces and also the balance of the moments. Okay, and I have introduced two rules to you that you can identify that the forces form an equilibrium situation. That is the concept of concurrent point, and also when they are able to form a closed polygon. So if there's other situation, if there's a situation where these forces are not able to form a closed polygon, and really they can't have a concurrent point, then we have to just rely on using the principle of moments and also the balance of the forces to solve the situation. So for example, a case of seesaw like that. Okay, so we're going to look at cases in, for example, the first one. So there's a plank, forces are labeled there, F1, F2, and mg, the weight of the toddler. So let's apply balance of forces in the y direction, because there shouldn't be any forces in x direction, so we just ignore that. So F1 plus F2 equals to mg. If that's in equilibrium, upward force equals to downward force, and total moment will be equal to 0. So to solve the balance of the moments, first you have to pick the right choice of the point of moment, POM. Point of moment, POM. Remember, the principle of moments tell us that we can pick any point as the point of moment and work out the clockwise moment and anti-clockwise moment. Okay, so if you pick this one, that will be F1 times 3L over 4 equals to F2 times L over 4. Okay, so let's consider another situation here. We have a mass 120 kg, and let's say that the beam is in equilibrium and the mass of the beam is negligible, and because it's hinged on the wall, so you should expect that there should be reaction force from the wall, and there should be tension pointing up. Reaction force from the wall is pointing up because if this thing is not falling, if this thing is not moving down, then there should be a frictional force that is trying to keep it upward, which is the arrow shown here. And then there's a downward force here. So once we identify all the forces, then we can start to solve the problem, which is finding the tension in the cable. So let's bring out the forces again. So the first thing, principle of moment tells us that the sum of moment at any point will be equal to 0. Then we pick a point of moment where we don't want. Again, the first step is we pick a point of moment where we do not need to find the unknown force, which is the reaction force here. So because we want to avoid two unknown in an equation, after that we identify the clockwise moment and also the anti-clockwise moment, which is caused by the weight and also the tension. Again, you can use the idea of using a pen. Use your finger to hold at the point of moment, and then you simulate where do they rotate. So once we got that, we have T times L, because the T is acting at a total of L, the length of L here, equals to mg times x. So this is basically the x, and then you sub in the values. Okay, then you will get 824. You can do the detailed calculation. Yeah. B, what is the force between the beam and the wall F? So now the question asks the unknown force that we ignored just now. So the force between the beam and the wall F. So there are two methods to solve this unknown, or to find this unknown. The first thing is, the first method is we use the balance of the forces. Since we already got the force of the tension just now, which is 824 Newton, then we can apply T plus F equals to mg, because T and F, they are both upward force and mg is a downward force. So if this beam is at equilibrium, the forces should be balanced in the y direction. So therefore, if you sub in the values, you should be able to find the 355 Newton. Okay, so if you don't understand, you try to replay the video, and if you get the wrong values of your answer, you can just check the error. So like I said just now, there's two methods to do this. The first one, we use balance of forces. The second one, we can still apply the balance of the moment, but now we pick the point of moment at where the tension acts, because that's the unknown that we don't want. So we form our equation of the balance of moment, mg times L minus x. Then L is total length, and x is the 7 meter here. Okay, then you get F times L, because F is L away from this point of moment, and L minus x for mg is because the distance of mg is this distance, the remaining distance after x is being taken out. Okay, so always take the distance of the distance for the where the force acting towards the point of moment. So you should get the same answer. Okay, let's move on to another example. So in this case, the simplified diagram, though it looked very complicated, but the simplified diagram is already drawn below here. So we have three forces, the R, F, and also the 50. Okay, so 50 basically is the weight of the bowling ball. The F basically is the tension in the bicep, and the R basically is the reaction force, okay, at this joint here. Okay, so this is the ulna. So as the ulna move, it should press at O in the upward direction, okay, on the humerus. So the humerus will give a reaction that is downward. That's why the R is downward here. Okay, we are going to find the tension in the muscle F. So let's use the balance of moment. So of course you can choose balance of the force and balance of the moment, but it depends on whether you can solve or you can find the unknown R's conveniently. So if you cannot find the value or the answer using the balance of force, then you go to balance of moment. If you cannot find using a balance of moment, but can straight away get very quickly the answer from balance of forces, of course you use the fastest way. Okay, so the point of moment, we're going to pick at the O here, because that's the R that we don't want. So F times X. So again, with regards, distance must be towards the point of moment X, and W is L. The whole length here is the L. Okay, so after we sub in the value, this is the this is the 0.350. No, sorry, this is given actually. This is the 0.03. M, that's right, W is 50, L is 0.350. Okay. What is R? So that's another unknown that is asked now. So again, you can use the balance of the forces, because we have already found the F. or you can still use the balance of moment that we pick the point of moment at F. Okay, so in this case, for balance of moment, you pick this as the point of moment. So I think there's a mistake here. This is supposed to be the R. Please correct that. Okay, so R times X, which is the 0.03, and then W is 50, L minus X because that's the remaining distance here. Okay, for W to times the distance to the point of moment, so this is the L minus X, which is 0.35 minus 0.03, and this is the L minus X. Then you should get 533. So on the other hand, you can also use the balance of forces to get the answer. Alright, so let's move on to one exercise that we have 400 kg, and then we are asked to find TR. So again, the same strategy that we figure out a point of moment where we don't want the unknown to affect our equation. So point of moment at TL, because we don't want that value first, probably will be asked later. Then we find out the necessary perpendicular distance from the weight to the point of moment, and then we form the equation mg times x. X is the 2 meter, and TR times L, where L is the 7 meter. Then you should get this answer of 1120 Newton. Alright, so question does not ask us to find the TL, but you can do that. Again, you can use the balance of force, or you can use the balance of moment, taking the point of moment at TR, and then you form the solution to check whether it's the same answer as the balance of the forces. Okay, that way you can do it on your own as a practice. So then I have two exercises after that. I need you to do this and submit as the homework. Okay, so take a picture and submit in the assignment in the Google Classroom.